Hello and welcome to this video. In this video we will continue our read through after string. We had covered the printing of string type bytes. So we had covered up to here, had covered this, and now we are going to study binary sequence types, bytes, byte array and memory view. So most of the functions are like strings. By the way, if you are new to the channel, make sure you subscribe to the channel and press the bell icon so that you can get notified about upcoming videos on Python and likes. So with that aside, let's continue. So the core built-in types for manipulating binary data types are bytes and byte arrays. So when you are dealing with bytes, the data types which we will use are bytes and byte array. For example, if you are modifying an image or reading any binary file, then bytes or byte array will be used. They are supported by memory view, which uses the buffer protocol to access the memory of other binary objects without needing to make a copy. Now, buffer protocol, if you want to study, then you have to go into the details of Python C API, and that is kind of out of scope for me. The array module supports efficient storage of basic data types like 32-bit integers and IEEE 754 double precision floating values. Bytes objects are immutable sequences of single bytes. Since many major binary protocols are based on the ASCII text encoding, bytes objects offer several methods that are only valid when working with ASCII compatible data and are closely related to string objects in a variety of other ways. Now, when we deal with bytes, what happens is that each byte will have value between 0 to 255. So it deals with that data byte by byte. And that's why ASCII compatible values can be easily represented in there. Unicode, not so much, because Unicode requires certain conditions which will not be met if you treat them byte by byte. Because in Unicode, you have to make sense of multiple bytes at the same time. So the efficiency is gone. Now, bytes can be converted by calling the bytes constructor with source encoding errors. Firstly, the syntax for bytes literals is largely the same as that for string literals, except that a b prefix is added. So the only change which we'll have with the string is b, which has to be prefixed for a string. Single quotes b still allows embedded double quotes. Double quotes b still allows embedded single quotes. Triple quoted b triple quote, three single quotes, triple quote b triple double quote, three double quotes. So this is how you can create byte strings in general. Only ASCII characters are permitted in bytes literal, regardless of the declared source code encoding. Any binary values over 1 to 27 must be entered into bytes literal using the appropriate escape sequence. As with string literal, byte literals may also use R prefix to disable processing of escape sequences. See strings and byte literals for more about the various forms of byte literal, including supported escape sequences. So we might hop on there and you can see the byte literal grammar here. So for raw binary, you can use BR or RB, and then your string literal will be raw encoded. The byte sequence will not be treated. So byte sequence for byte literals are basically these, I guess. Yep, these are the byte sequences. We have already studied this, so if you feel like, you can go back in the playlist and watch the previous video to know about escape sequences. While byte literal and representations are based on ASCII text, byte objects actually behave like immutable sequence of integers, with each value in the sequence restricted such that 0 less than equal to x less than 256. Attempts to violate the restriction will trigger value error. This is done deliberately to emphasize that while many binary formats include ASCII based elements and can be usefully manipulated with some text oriented algorithms, this is not generally the case for arbitrary binary data. Blindly applying text processing algorithms to binary data formats that are not ASCII compatible will usually lead to data corruption. In addition to the literal forms, a bytes object can be created in a number of ways. A zero-filled bytes object of specifying length bytes 10. From an iterable of integers bytes range 20. Copying existing binary data via buffer protocol bytes supplied with object. Also see the bytes built in. So we have built-in function bytes. We have studied this. So we will not go in there. Since two hexadecimal digits compose precisely to a single byte, hexadecimal numbers are a commonly used format for describing binary data. Accordingly, the bytes type has an additional class method to read data in that format. The class method is called fromHex. It can read from string and give you a bytes object. So bytes dot fromHex, you give it byte string and you get a byte. You get the encoded byte string. A reverse conversion function exists to transform a bytes object into a hexadecimal representation. So if you have a byte string like this with hexadecimal values f0, f1, f2, then you invoke hex on that and you will get a string of hexadecimal numbers. If you want to make the hex string easier to read, you can specify a single character conversion separator sep parameter to include in the output. By default, this separator will be included between each byte. A second optional bytes per separator parameter controls the spacing. Positive values calculate the separator position from the right, negative values from the left. So for example, if you have a byte string like this, then you can say value.hex minus, then backslash x will be replaced with minus. So the byte string you can read as f0 minus f1 minus f2. And if you want separator, then positive value you give 2, that is calculated from right, and at that position underscore will be replaced. And from left, if you give, so if you give minus 4, then after 4 bytes it will be placed. Since byte objects are sequences of integers akin to a tuple for a bytes object, bytes object b0 will be an integer, while b0:1 will be a bytes object of length 1. This contrasts with text strings, where both indexing and slicing will produce a string of length 1. The representation of bytes object uses the literal format b triple dot within single quote, since it is often more useful than example bytes 46, 46, 46. You can always convert a bytes object into a list of integers using list b. So if you pass a bytes object to a list constructor, then you will get a list object, list of integers. Byte array objects are a mutable counterpart to bytes object. So bytes are immutable while byte array is mutable. Bytes are immutable and byte array is immutable. Class byte array with source, encoding and errors. There is no dedicated syntax for byte array objects. Instead, they are always created by calling the constructor. Creating an empty byte array is like this. Creating a zero-filled instance with the given length byte array 10. From an table of integers byte array range 20, copying existing binary data via the buffer protocol byte array, you give byte string high. As byte array objects are mutable, they support the mutable sequence operation in addition to the common bytes and byte array operation described in bytes and byte array operations. We'll see this in a bit. There's a built-in also, which we have already covered. Since two hexadecimal digits correspond precisely to a single byte, hexadecimal numbers are commonly used format for describing binary data. Accordingly, the byte array type has an additional class method to read data in that format. So fromHex and hex is similar to bytes. Since byte array objects are sequenced to integers, this is the same information which we read for bytes. So I will skip this. Now we come to bytes and byte array operations. Both byte and byte array objects support the common sequence operations. They interoperate not just with operands of the same type, but with any bytes like object. Due to this flexibility, they can be freely mixed in operations without causing errors. However, the return type of the result may depend on the order of operands. Now note, the methods on bytes and bytes object Byte array objects don't accept strings as their arguments, just as the methods on strings don't accept bytes as their arguments. For example, you have to write, if A is a string ABC and you write B is equal to A dot replace A with F, then in bytes you have to prefix everything with B. So ABC will be prefixed with the B, A will be prefixed with the B, and F will be prefixed with the B. Otherwise it will not work. If you don't give this B, then it will be treated as a string and it will not work. Some bytes and byte array operations assume the use of ASCII compatible binary formats and should be avoided when working with arbitrary binary data. The restrictions are covered below. Note, using these ASCII based operations to manipulate binary data that is not coded in ASCII based format may lead to data corruption. The following methods on bytes and byte array objects can be used with arbitrary binary data. Now remember that whatever we are going to cover henceforth for bytes and byte array, we have already covered for string. So most of this will behave in the same way as it behaves for strings. Okay. So if you have not watched the previous video on string, which I have covered in I think 2 or 3 videos, you should better go and cover that, because I will not be giving examples of all these. I'm just going to read through this. So byte.count or bytes array.count return the sub number of non-overlapping occurrences of subsequences sub in the range start end. Optional arguments start and end are interpreted as in slash notation. The subsequence to search for may be an bytes like object or an integer in the range 0 to 255. If sub is empty, return the number of empty slices between characters, which is the length of the bytes object plus 1. Bytes.remove prefix or byte array.remove prefix. If the binary data starts with the prefix string, return bytes len prefix colon. Otherwise, return a copy of the original binary data. So this we have already seen in strings. This also we have seen in strings. Remove prefix. If the binary data ends with suffix string and that suffix is not empty, then bytes colon minus len suffix. Otherwise, return a copy of the original binary data. Bytes.decode. We have seen strings str.encode. Similarly, we have bytes.decode. So the default encoding is UTF-8 and errors we have already covered. So I'll skip this. Ends with a suffix. So it returns true if the binary data ends with the specified suffix, otherwise returns false. Suffix can also be a tuple of suffixes to look for. With optional start, test beginning at that position. With optional end, stop comparing at that position. So this we have already seen when we are discussing with strings. Similarly, we have seen find, index, both we have seen. So index, return the lowest index in the data where the subsequence sub is formed, such that sub is contained in the slice s start colon end. Optional arguments start and end are interpreted as in slash notation. Return -1 if sub is not found. The subsequence to search for may be any bytes like object or an integer in the range 0 to 255. Note, the find method should be used only if you know the position of sub. To check the sub, if sub is a substring or not, use the in operator. This is a similar example like we had for strings. Bytes.index, it is similar to our string.str.index, like find, but raise value error when the subsequence is not found. And the subsequence, this is the same text which is getting repeated. Bytes.join, it takes a table as an argument. Return a bytes or byte array object, which is the concatenation of the binary data subsequence of in a table. A type error will be raised if there are any values in a table that are not bytes like objects, including str objects. The separator between elements is the contents of the bytes or byte array object providing this method. Make trans, we have seen this is a complicated one to exemplify. So I have already exemplified this for str. This static method returns a translation table used for bytes.translate that will map each character in from into the character at the same position in 2. From and to must both be bytes-like objects and have the same length. Partition is similar to string. Split the sequence at the first occurrence of separator and return a 3-tuple containing the part before the separator itself or its byte array copy, and the part after the separator. If the separator is not found, return a 3-tuple containing a copy of the original sequence followed by 2 empty bytes or byte array objects. So this example we have already seen for str, so I will not exemplify any of these. Replace. Return a copy of the sequence with all occurrences of subsequence old replaced by new. If the optional argument count is given, only the first count occurrences are replaced. The subsequence to search for and its replacement may be any byte-like object. The byte array version of this method does not operate in place. It always produces a new object even if no changes were made. So this we have to keep in mind when we are dealing with byte arrays. rfind is the reverse of find, that is, it operates from end. Rindex operates from the end. Rpartition operates from the end. Starts with. Return true if the binary data starts with the specified prefix, otherwise return false. Prefix can also be a tuple of prefixes to look for, with optional start test beginning at that position, with optional end stop comparing at that position. Translate is similar to what we had studied for str.translate. Return a copy of the bytes of byte array object where all bytes occurring in the optional argument delete are removed and the remaining bytes have been mapped through the given translation table, which must be a bytes object of length 256. You can use the bytes.makeTrans method to create a translation table. Set the table argument to none for translations that only delete characters. So for example, a byte string is reach this short text, translate is none, and the byte string is AEIOU. So all the vowels are deleted here. The following methods in bytes and byte array objects have default behaviors that assume the use of ASCII compatible binary format but can still be used with arbitrary binary data by passing appropriate arguments. Note that all of the byte array methods in this section do not operate in place and instead produce new objects. So this is similar to strings, but the only difference is that they produce new objects and don't operate in place. Center function is return a copy of the object centered in sequence of length width. Padding is done using the specified fill bytes. Default is an ASCII space for bytes objects. The original sequence is returned if width is less than or equal to len as. The byte array of version does not operate in place, but it produces a new object. Ljust, it justifies the string byte sequence to the left side, okay, and the width is specified by width, and fill bytes specifies the bytes with which to fill. Lstrip will remove the spaces on the left side, and rstrip will remove the spaces on the right side. So the corresponding function to lstrip is rstrip. So you can see the examples how lstrip removes this spaces and how this removes www from big left side. So note that lstrip, if you use here like this, then it will also remove thr from here, okay, but remove prefix will not do that. Remove prefix will do an exact match. Rjust does the right justification. Splits from the right side. Rstrip is similar to lstrip, as you can see. Split. So we have not covered split, but rsplit was given before. So we will first see the split. It is similar to our string operation. Split the binary sequence into subsequences of the same type using separator as the delimiter string. If max split is given and non-negative, at most max splits are done. Thus the list will have at most max split plus 1 elements. If max split is not specified or is -1, then there is no limit on number of splits. All possible splits are made. If separator is given, consecutive delimiters are not grouped together and are deemed to delimit empty subsequences. For example, binary string 1 comma 2 dot split b comma returns b1 b empty string b2. The separator argument may consist of multi-byte sequence. For example, bytes 1 less than greater than 2 less than greater than 3 split b less than greater than returns b1 b2 b3. Splitting an empty sequence with specified separator returns b empty string or byte array b empty string depending on the type of object being split. The separator argument may be any byte slice object. Some examples are given which you can read for yourself. If separator is specified or is none, a different splitting algorithm is applied. Runs of consecutive ASCII white spaces are regarded as a single separator, and the result will contain no empty strings at the start or end if the sequence has leading or trailing white space. Consequently, splitting an empty sequence or a sequence consisting solely of ASCII white space without a specified separator returns empty list. So once you have understood the split, the R split will happen from the right side. So max split will come into picture when you are doing R split. So you should be careful about that. A strip will remove from left side and right side both sides. White spaces will be removed from left and right both sides. Otherwise, the characters will be removed. If you supply characters, then it will be removed from left and right side both. Capitalize will return the capitalized version of the binary bytes object or byte array object. Expand tabs will expand tabs with spaces. The default is the tab size default is 8, but it can be 0, 8, 16 and so on. Is alphanum will replace if the character is a byte is alphanumeric. Is alpha will return true if it is alphabet. Is ASCII will return true if it is between 0 to 127. Is digit will return if it is 1, 2, 3, 4 and 9 or 0. Is lower will return true if it is a lowercase character. Is space will return true if it is an ASCII white space. Is title will return the title case string as true and non-title case as false. Is upper will return true if all characters are uppercase and false if all are not uppercase. Lower will return a copy of the string converted all to lowercase. Split lines we have covered this in string in great detail. So it will split the binary string into different strings of list of different strings. Swap case will return a copy of the sequence with all lowercase ASCII characters converted to their corresponding uppercase counterpart and vice versa. So it will just flip the cases of the characters. Title will return a title case string. For example, this hello world will be hello world with capital W. So the algorithms these we have studied. Upper will convert everything to uppercase. Zfill will fill with 0. So most of these functions we had studied in strings. So if you think that I have skipped some of these, then that is the reason, because we have covered it in the strings one and we have in a similar fashion. So I would recommend that you go 2-3 videos earlier and look in the playlist. That is, if you look at the Python 3 programming playlist, 2-3 videos earlier we have covered all these functions of strings and I have shown the examples. That is why I have skipped the bytes and byte array. And printf style bytes formatting is similar to string style byte formatting. The only difference is you have to prefix it with b. So that's the only difference, otherwise it's the same. So I will skip this also, and in the next video we will continue with memory views. So with this I will end this video here. I hope that you have found this video useful and informative. I feel like I feel apologetic that I did not cover this in great detail about bytes because I had covered this for strings. So please like the video, share it on social media, and make use of the comment box to for suggestions and improvements. Or otherwise, you want to just chat, make use of comment box. Thanks a lot for watching. Happy programming.